In the previous video, we talked about the relation between the position of an element in the periodic table and its electron configuration. We will soon see that the number of valence electrons that an atom has determines how it can connect with other atoms. The number of valence electrons that an atom has is important because atoms connect either by sharing electrons or by passing electrons to each other. In addition to the number of electrons that an atom has, how it bonds with other atoms is also determined by how strongly it holds on to its electrons. The atoms of some elements give up their electrons more readily than atoms of others. Atoms of other elements are more likely to grab extra electrons from the atoms they bond with. How easily an atom gives up one electron is characterized by a quantity called the ionization energy. A larger ionization energy means that it is harder to remove an electron from the atom. The position of an element in the periodic table tells us something about ionization energy of its atoms. As we move from left to right within a period, the ionization energy of the elements increases. For instance, if we consider elements within the second period, lithium will give up its only valence electron, the electron in the 2s subshell, relatively easily, but fluorine will hold on to its 7 valence electrons, 2 in the 2s subshell and 5 in the 2p subshell, very strongly. Therefore, the ionization energy for lithium is lower than it is for fluorine. As we move from top to bottom within a group, the valence electrons will be located in larger and larger orbitals. Remember, the single orbital in the 1s subshell is the smallest s orbital. The single orbital in the 2s subshell is larger. The single orbital in the 3s subshell is yet larger, and so on. The trend is the same for orbitals in other subshells. That is, the orbitals in the 3p subshell are larger than the orbitals in the 2p subshell, and so on. Electrons that are located in larger shells are on average farther away from the nucleus and are held by it weaker. Therefore, it is easier to remove an electron from shells that correspond to larger principal quantum numbers, and the ionization energy decreases as we move down within a group. For instance, in the second group, beryllium has the largest ionization energy. The ionization energy for magnesium is smaller. The ionization energy for calcium is still smaller, and radium has the smallest ionization energy. Thus, it is easy to compare ionization energies for two elements that are within the same period. It will be larger for the element farther to the right. It is also easy to compare ionization energies for two elements that are within the same group. It will be smaller for the element that is further down. But what can we say about the ionization energies of two elements that are neither in the same period nor in the same group? For instance, can we determine whether barium, atomic number 56, or lithium, atomic number 3, has a larger ionization energy just by looking at their positions in the periodic table? The answer to this question is no, generally not. We know that the ionization energy of lithium is larger than that of cesium, an element that is also in the first group but below lithium in the sixth period. We also know that the ionization energy of barium is larger than that of cesium because it is to the right of it in the same period. So we know that the ionization energies of both lithium and barium are larger than the ionization energy of cesium. Unfortunately, that tells us nothing about how the ionization energies of lithium and barium compare to each other. Therefore, one can't compare the ionization energies for elements that are neither in the same period nor in the same group by just looking at their positions in the periodic table. In such cases, one would need to look at the values of the ionization energies for both elements, and those can be found in special tables. The ionization energy of an element is related to what is referred to as its metallic character. Metals tend to give up their electrons more easily than nonmetals. Whereas the ionization energy increases from left to right within a period and decreases from top to bottom within a group, the metallic character behaves in the opposite way. It decreases from left to right within a period and decreases from bottom to top within a group. Therefore, with the exception of hydrogen, elements on the left-hand side of the periodic table are metals, and elements on the right-hand side of the periodic table are nonmetals. The majority of the elements in the periodic table are metals. They are classified into the following families. All elements in the first group are alkali metals. These elements only have one valence electron and they readily give it up when bonding with other atoms. All elements in the second group are alkaline earth metals. These elements have two valence electrons. They give them both up rather easily when bonding with other atoms, but not quite as easily as the alkali metals. All elements in the D block, groups 3 through 12, are transition metals. They give up variable numbers of their valence electrons when bonding with other atoms. How many electrons they give up depends on the element with which they are bonding and other conditions. To the right of the D block, there is an irregularly shaped block that spans the lower part of groups 13 through 16. The elements in this block are so-called post-transition metals. They usually give up their electrons to other atoms when bonding with them. However, in some cases, they also show a tendency toward sharing electrons with other atoms rather than giving electrons up completely. Metals share certain properties. All metals except mercury are solid at room temperature, although they can be melted at higher temperatures. The melting temperature for metals varies greatly. Gallium will melt from body heat when held in the palm of the hand, whereas melting tungsten requires a temperature of nearly 6200 degrees Fahrenheit. Metals also tend to be lustrous or shiny, and they conduct electricity and heat. All of these properties are actually determined by the electron configuration of metals, although we will not discuss how exactly in this class. Above and to the right of the block of post-transition metals is a block of so-called metalloids. Atoms of metalloids tend to share electrons with other atoms rather than to give them up completely, as atoms of metals do. This tendency leads to properties that distinguish metalloids from metals. Metalloids are not very good conductors of electricity. For instance, the metalloids of group 14, silicon and germanium, are the most important semiconductors that conduct electricity under certain conditions that can be controlled. These elements, especially silicon, are the principal materials of the semiconductor electronics industry. All metalloids are solids, but unlike metals, they tend to be brittle. That is, they will crack rather than bend when one attempts to deform them. Elements in a triangle at the top of groups 14 through 16, carbon, nitrogen, oxygen, phosphorus, sulfur, and selenium, as well as hydrogen, are nonmetals. Whereas metals and metalloids tend to form bulk atomic crystals, where huge numbers of atoms of the same element are joined together in a regular pattern. Nonmetals have the ability to form materials where only a relatively small number of atoms of the same element form a homoatomic molecule. A molecule is a group of two or more atoms that are chemically joined together in a regular pattern. Like atoms, molecules are also electrically neutral. The adjective homoatomic, also referred to as homonuclear, describes a molecule that consists of atoms of just one element. We will discuss how atoms bond together to form molecules in considerable detail in the second part of our course. Molecules of nonmetals may stick together to form molecular solids or fly around in free space, forming gases. The elements in group 17 are the halogens. They exist in the form of diatomic homoatomic molecules. The adjective diatomic means consisting of two atoms. The molecules of fluorine and chlorine form gases at room temperature. The molecules of bromine form a liquid. It is the only element except mercury that is liquid at room temperature. The molecules of iodine and astatine form solids. When combining with elements of other elements, halogens are very good at taking electrons from them. The elements in group 18 are noble gases. Their atoms do not like to combine either with each other or with atoms of any other element. Therefore, they exist at room temperature as atomic gases, single atoms flying around in free space. So far, we have talked about the chemical elements and substances that are made of atoms of only one chemical element. We only know 118 chemical elements today, of which 94 occur naturally on Earth. However, the variety of substances that make up both non-living and living things around us is much greater. Most substances are made of atoms of different elements that combine together in defined ways to form chemical compounds. We will talk about chemical compounds in the second part of this.